Hey, good morning to one and all. So welcome to another session of DSP Algorithms and Architectures. So in this session, we will start off with the discussions of the architectures of the programmable digital signal processing devices. So architecture in the sense, we have seen microcontrollers or microprocessors. So when we speak about microcontrollers or microprocessor, there will be some elements which are present which will make up that entire microprocessor or microcontroller. So that entire thing we can classify it as the architecture. Similar kind of thing is available even for the DSP devices. So as we have in microcontroller, right, we have arithmetic unit, we have a logical unit, then we have the bus architectures, which help us to fetch the instructions and fetch the data from the data memory. So then apart from that, again, we have say logical aspects, how the interconnection goes on. So some mux might be there, some address lines might be multiplexed. So such kind of things are present. So how do I cater to these things with respect to digital signal processing devices? Now, microcontroller and microprocessors are very basic elements. They are not suitable for very high speed operations. That would take a lot of time for it to process. Then apart from that, power dissipation also might be a problem when we are speaking of your regular microcontroller or microprocessors. So therefore, what happens is there is a need for some other architecture so that we can cater to all these problems. We can address all these problems. For example, if you just see in digital signal processing subjects or relevant operations, you see that, for example, you observe convolution. In convolution, what is happening? You can see that it is a summation of some product element. Say x of n convolved with h of n. So it is summation of x of m into x of n h of n minus m. So we have the shifted version of the filter coefficient. Then we have the input signal x of n multiplied multiply those and then add those. So it is like a repetitive operation which is present over there. So because of this one, we get another concept like something called as multiply and accumulate. So that is what we get. So we multiply and add. So it is multiply and accumulate. So this is a few concepts which are present in DSP. So majority of the processing is done in this form. So in order to cater to these things, we have to look into what are the different architectures which are present. So from programmable DSP devices. So what is a basic architectural feature? So whenever we speak of programmable DSP devices, they have some instructions which are similar to microprocessors, but they have few special instructions which are specifically for DSPs. So one example I gave that you have say a convolution operation, which is a summation of the product elements. So there also in microprocessor also we have say MUL instruction, then we have add instruction. But here, can I take the advantage of some other features over there? That is what we have to look out for. So here, what we are doing is we can use few of the instructions which are present in microprocessor architecture in order to implement, but we can at the same time, we can have some improvement on those. So that is what we'll be looking out in this entire topic. Then what are the basic capabilities which these instructions could provide? So those are nothing but again the same this thing what we have arithmetic operations, logic operations. Then we have one special this thing that is multiply and accumulate. So best example would be the convolution operation what you are performing. So you are multiplying and you are adding, multiplying, adding. So that is what you are doing. So you are multiplying and accumulating the result. So that architecture will just have a look in the coming forth slides. Then we also require to scale these signals. Even the coefficients also have to be scaled. So here, whether it is the input signal or the output signal, sometimes scaling operation becomes necessary. So how these scaling operations are being implemented in DSP. So that is what we will be looking out in this entire topic. So here we have specified all these things, right? Arithmetic, logic, multiply and accumulate, that is MAC, and signal scaling operations. These all can be implemented by having a dedicated hardware. Now, when we have a dedicated hardware for these operations, what happens is hardware implementation will have hardware implementation will help us to achieve better speed. Will help us to achieve the better speed. That is, we'll be able to get the results at a very faster rate. So, and power dissipation also can be minimized. I cannot tell that it will be totally eliminated. It can be minimized. So that is what we do in DSP. In a regular microprocessors, you might not have dedicated hardwares for say multiply and accumulate or signal scaling operations. Just for example. So what you do is you use the instructions itself and you try to implement it. So from a software point of view, try to achieve the results. So you go for looping instructions and then you go ahead. So that is what you do in your microprocessors. But here you provide a dedicated hardware for these operations. Then what are the different support architectures which should include the hardware features? So here we can have different, along with the previous features, we can have different kinds of memories also provided. That is, we can have on-chip registers which will help us to store the results. Say in multiply and accumulate, at each step I'll be getting some alternate results. So intermediate results I need to store. So that I can again achieve with the on-chip registers. Then we have on-chip memories which help us to deal with the signal samples. So it may be a scaled version or non-scaled version. So dependingly. Then we have on-chip program memory. We can have these things in which programs and fixed data will be present. So that is what we'll be doing. So it is similar like your system in which you have a cache memory in which some parameters come and sit in so that the execution becomes fast. So along with that, you have the other memory. So these are the kinds of architectures what we can look out for. So we'll be having RAM, ROM, and the register part and the registers. So these are the things what we'll be having. Or these are the things which are basically required when we are thinking of DSP devices. So here we can just look at this equation. What is the question over here is, so for this FIR filter, nth order FIR filter, what are the basic features that should be provided for DSP architecture? So looking at this equation, we can, so basic features in the sense, these things we have to check out. What all, whether I require a MAC unit, whether I require a scaling unit, whether logical operation, whether arithmetic operation, or whether I require the registers, memories, and the chip memory for programs. So these are the things, that is RAM, ROM, or registers. So registers for intermediate results, memories for the signals, and on-chip memory for programs and fixed data. For example, for the filter coefficients. So if I write x of n convolved with h of n, here h of n is the filter, and the coefficients relevant to these are the filter coefficients. So these coefficients will be will be stored in the ROM, whereas this signal x of n will be present in the RAM. That is what they are specifying. So here we can see that based on this equation, first thing you require a multiplier. Then because there is a summation, you require an adder. Then apart from that, if I just see, it is nothing but multiply and accumulate unit which is required. So because summation, it is like if I write it, it is h of 0 into x of n plus h of 1 into x of n minus 1 and so on up to this point. So what is happening? Filter coefficient multiplied with signal added with this next filter coefficient into the signal, which gets accumulated with this result. Similarly, the next one. So it keeps on adding, multiplying and adding. So it is like multiply and accumulate aspect. Then apart from this, I require memory to store x of n, and I require memory to store the filter coefficients. And apart from that, I require memory to store the result. So three things we can observe here. So that is memory to store the signal samples, then memory to store the filter coefficients, and memory to store the intermediate results or the final result. So this is another thing. Then I require the multiply and accumulate. That is, I require a hardware multiplier and a adder in order to carry the multiply and accumulate operation. That is what I spoke about in this case. Now, when we are speaking of these things, what other things come into aspect? So here, since we have to keep the accumulator results, right? We have to keep on accumulating the results. So I should have a register for that purpose. So one register especially for accumulation. So which will be just keeping track of those things. Now, apart from this, what happens is we should have pointers to point which values have to be accessed next, or which values are being accessed. So to keep track of those things, I should have two pointers, one pointer pointing to the signal and one pointer pointing to the filter coefficients. So that is what we have, a register which points to the current signal sample that is being used. So we can call it as a signal pointer, and another one is the coefficient pointer. So in which register will be storing the current, say, address or the filter coefficient that is being used. So next we have a register which will keep the count of MAC operations. So how many MAC operations are being conducted and how many are remaining. So that information can be obtained from this register. Now, if scaling is required, then I should perform that scaling operation also. So, and based on that, the computation of y of n is obtained. And when we are storing it back into the memory, then we require shifters at the input and the output. So scaling operation is performed using these shifters. So that is what we are trying to say. If I have something like this, if I shift it, it will be scaled by a parameter of, so this will be it will be 1, 1, 0, 1, 1. If I'm scaling it, it will be half. So I am scaling it by half. Or if I want to increase it, then I shift it in the other direction. It will be doubled. So something of these things. So it is required because you had studied that mantis and the exponent part. When we are multiplying, what happens is the exponent part of the number should be same. Otherwise, when we are doing addition or some other operation, multiplication will not create problem. Addition will create problem. Suppose I want to add a number as 0.2 into 10 raised to minus 1 plus 0.1 into 10 raised to minus 2. So in order to add this, what we do is we have to make the exponents same. So in order to perform this, again, scaling operation might be required, or we have to just check out these things and then go ahead. So that's why we require shifters in these cases. So what are the basic features that would be required for the DSP architecture of this FIR filter, nth order FIR filter? First one, memory to store the coefficients, memory to store the signals, and memory to store the intermediate results, or registers to store the intermediate results. Then I require a multiply and accumulate unit which performs the operation of multiplication and addition. So once this is done, at each level, I keep on accumulating the result. So I require an accumulator. I require an accumulator which keeps on accumulating the intermediate results. Then I require a counter which keeps track of how many MAC operations are being done or how many MAC operations are pending. So that is another this thing which is required. Then apart from that, I should have registers which point to the current coefficient of the filter and another register which stores the current value of the signal which are being processed over here. So these are the few things which are required. And apart from that, if scaling is required, then we would require the shifters at the input and the output. So these are the things what are required for DSP architecture for implementation of this nth order FIR filter. So in this one, these are the things what we discussed. So we have all these things: arithmetic operations, logic operations, then multiply and accumulate, signal processing, signal scaling operation. Then apart from that, we have the memories, that is RAM, ROM, and the registers. So with respect to this, we discussed this example. We have discussed this example. So these are just basic architectural features of a DSP device. So next we go in depth of the DSP computational building blocks. So in the previous listing we discussed like Mac and other stuffs, right? So that is what we'll be discussing over here one by one. So what each consists of, how we can go ahead with its existence. So what can be done. So these are things what we'll be discussing. So here we have the DSP computational building blocks. So using these building blocks, I can implement the DSP operation. I can implement the DSP operation. Suppose I want to implement, say, multiply and add together. So in order to do that, I can go ahead with the MAC unit. So which will do multiply and accumulate operation. So we'll by looking at the structure, we'll get to know what exactly is happening in this. So they will be checking out those things. And if I want, say, just a arithmetic operation, so I go ahead with the ALU block and try to implement what is required. So multiplier, how do I implement? Shifter, how do I implement? So those all things we'll be looking out in these cases. Now, these hardware building blocks are built depending on what is the functionality which is required, what is the operational speed which is required, how fast you want to operate, and how quickly you want the results, and what is the accuracy which is required for that implementation. Suppose you're doing some operation and I want to display numbers up to 3 decimal points. So this can lead to precision and the accuracy requirements. And if you're not able to provide this one, then your system might not be useful in that case, because a minor change would affect the system. So that is what we have to look out for. So whenever we are looking out for the hardware building blocks, these are the things what we try to keep in mind and build those hardware building blocks based on the functionality what you want to implement. Say whether you want to add, whether you want to multiply. So those are the functionalities. Then what is the speed requirement? So how quickly I can get the result for the input what I have given, or how quickly the operation can be performed, and what is the accuracy and the precision requirements. So these are the things what we have to look out when we are going ahead with hardware building blocks. So here we have these building blocks can be built to be general, or they can be built to be application specific. So we have something called as application specific ICs. So if for only specific application, so we have say IC, and this IC performs only convolution operations. So this is for only specific operation. But if I have some device which takes the input, and if you want say to implement addition, you have a block; to implement multiplication, you have a block, and using these two blocks, say for example, I can go for convolution, then I can get the results. So this one is not specific, it is in general. So these building blocks are basically built to be general, and they can also be specific also, but we'll just check out. But in this one, they are built to be general so that many applications can use it. They can use this and build the logic what they want to implement. And they are built to be easily integrated with the DSP blocks, what we'll be discussing. So few essential basic building blocks which are required to carry out the DSP computations are multiplier, shifter, MAC unit, and ALU. So these are few things. So these we'll be discussing in the coming 4 sessions now. So coming to the multiplier part. So whenever we speak of multiplication, how do we go ahead with multiplication? Say let us consider that these are the two numbers, that is A and B. I want to multiply these two numbers. So if it is binary also, whether it is in binary or whether it is in decimal form, the multiplication steps remain same. So here we have B naught multiplied with A naught, B naught multiplied with A1, B naught multiplied with A2, and B naught multiplied with A3. So this A naught into B naught gives you the first number here, then the next number, then the third number, and the fourth number. So then what we do, we shift it. We shift for the next this thing. So B1 multiplied with all these four. So we have these four numbers. Again, we shift by another location. So these are what we are having. So at the last, we have these. So this is how the implementation goes ahead. And what we do is we add all the numbers and get the overall product. So P0, P1 up to P7. So here, if we have say n bits here and n bits here, then we'll be having, you can see that it is for 4 bits, you can have a max of 2 times 4, that is 8 bits. So here, if we want to implement it using a parallel multiplier, so this is your regular multiplication approach, what you have. So how do I go ahead with the hardware part? How do I go ahead with the hardware part? So here we'll check out with the multiplier in hardware. So this is a binary representation. So this is binary representation of the number. So we have a number A, which is AI into 2 raised to I. We have another number B, which is Bj into 2 raised to J. And say this is n minus 1, 0 to n minus 1 means this is n bits, and this is 0 to n minus 1 means this is m bits. So when we multiply these two, when we multiply A and B, so it is like, suppose I'll be having this one, it will be summation J is equal to 0 to n minus 1 Bj into 2 raised to J. Now, since this is dependent on J, I can take this summation outside. So if I take the summation outside, this is how it will be represented. Then what I'll be having AI into Bj and 2 raised to I into 2 raised to J. So which will lead to this result. So here you can see that exponent value I plus J, I and J get added, and here these two get multiplied. These two get multiplied. So this is nothing but what? It is the shifting operation. This leads to nothing but shifting operation. For example, if I have a number as 1, 0 in binary, and if I multiply it with binary number, what is the number I'll be getting? I'll be getting the number as 1, 0, 0. So it is 2 into 2, which is equal to 4. So it is nothing but this number what I have, 10. If I shift it this side, so it will be 1, 0, 0, which is equal to 4. So it is kind of shifting operation what we are observing. So that is what we have here, all the shifted versions. And these are the products of this mantis I could specify. So these are the mantissa values. So these are the mantissa products what we have, and this is helping me to identify what is the shift I should be having for the next number. So these are the two numbers A and B. When I multiply, this is the product what I'll be getting, in which these two get multiplied and the exponent value gets added. And since it is binary, we are taking it as 2. Okay. And this is n bits and this is m bits. So before going to this, we'll just check out this one. So based on that previous this thing itself, so if we just check out, what happens is, so we have what here. So first one is A naught B naught directly. Then we have what A1 into B naught plus A naught into B1, which gives you this result. So similarly these. So if I try to implement this in this form, you can just see what is the overall result I'll be getting. So here, if you just observe, so this is the first one. This is the next, and next result. So that is the first part. And then these are the next results what we have. So similarly, we have for the third listing, and this one is the last one what we have. So based on that, these are the things. So these act as input to these hardware adders. These are the hardware adders. So they act as input. So the first one does not require any adders. So directly I'll be getting the first result. But the next one is what? It is A1 B naught into A naught B1. A1 B naught into A naught B1. So whenever I add this, I'll be getting the overall result. So here we have one additional 0, that is, so here we can see that these adders are 3-bit adders. They are taking 3 inputs and they are providing 2 outputs. They are providing 2 outputs. So here again we can see that the result of this one gets added with this part, and whatever result is obtained from the previous step based on the shifting operation, here we will not be showing any shifting operation. So based on these two numbers and this number, we'll be getting the overall result, and there will be one additional parameter which will be coming from the this adder. So this one will continue in this form, and at the end I'll be getting the overall results. So here you can see that in the last operation, I'll be getting one result and another result which is related to P7. So this one is called as a Braun multiplier. So in this Braun multiplier, what we have adders which take 3 inputs and provide 2 outputs. It takes 3 inputs and provides 2 outputs. And for a 4 by 4 bit, that is 4 by 4 Braun multiplier, we can see that how many distinct multipliers are there. There are totally 12 multipliers, in of which we have 3 inputs and 2 outputs for each of the multiplier. So this is the Braun multiplier which gives us the parallel result. Now coming back to this part, what we have now, whenever we are doing multiplication of signed numbers, so what happens is we don't have any specific this thing wherein I can in register or in memory I can store this minus or plus symbol. I don't have this option. I can store only zeros and ones. I can store only zeros and ones. So how do I cater to this problem? So the best solution what they do is they go for 2's complement representation. They go for 2's complement representation. So because in this one, what happens is sign is taken care by the number itself and no need to use this minus or plus. So it is the universal rule what you will be following. Represent the number in 2's complement, whether it is addition of the numbers or subtraction of the numbers, always in 2's complement you add the numbers. Always in 2's complement you add the numbers. So this is why you go for 2's complement whenever you're speaking of signed. If it is unsigned number, no need to worry. Directly you can go ahead with the addition or subtraction which is there. But if it is signed numbers, what would happen is storing the minus or plus symbol is difficult. So that therefore, in order to overcome such kind of problems, what we do is we represent the numbers in 2's complement. Now, the Braun multiplier, what we spoke, right? That is the basic commercial implementation which is used for signed multiplications. So again, we have again different versions of multipliers, which are modified versions of the Braun multiplier, which again it is called as Bob-Woolley multiplier. Again, we have different multipliers also. So in this one, we'll just be looking at Braun multiplier. So whenever we are speaking of signed numbers, right? Whenever we are talking of these signed numbers, what happens is the first bit which is there, that is the MS bit, it always represents the sign information. It represents the sign information. And rest all give you the magnitude information. Rest all perform the magnitude information. Now, so here, one thing, as we had seen in this one, right, we had something as minus 1 raised to s. If s is 0, this will be 1, and if s is 1, this will be minus 1. So we had seen those things, right? The same kind of implementation we can see over here. So this is your mantissa part, and this is your exponent part. So whenever we represent it in this form, this is how it represents. Now, if the number is positive, for example, I'll take 0, 1, 0. So if I have this number, this if I specify it to be a sign number, the MS bit will be utilized for sign. So it will be 0 means plus, this is plus 2. Now, if I have something as this one, then 1 means what? It is minus 2. It is minus 2. So here, that is what they have specified. If a of m minus 1 is 0, it will be a positive number. If it is 1, it will be negative number. So this will come out as minus 1. So that is what we will be having over here. Okay. Now, instead of in previous case, what we did, we multiplied the unsigned numbers. That is here we multiplied the unsigned numbers. We did not consider the sign. But here we are considering the sign. So if you multiply A and B, so this entire thing multiplied with this entire thing, what you have? We have this number multiplied with this. That is what the first one is giving. That is the first element. Then we have this number multiplied with this one. So that is this part. Similarly, when I multiply this one with this is the result what I'm getting. And lastly, multiplication of these two, which is presented over here. So this is how it goes ahead. And you can see that when I multiply a number with m bits and n bits, the maximum numbers that can, the maximum bit size would be m plus n bits in the product. So it can lead up to m plus n bits. So it is based on this equation what the multiplier, Braun multiplier, what we saw in the previous slide, is dependent on. It is dependent on. So we are not going in depth of that. We are just seeing based on this equation, we try to just analyze it, but it is not exactly this equation what they are using. It is based on this entire thing because you're going for signed multiplication. So when signed multiplication comes in, so this is the equation what we'll be using. So this is just for reference. I had utilized it so that it becomes easy for just for the analysis purpose. So it is this equation what we have used in the Braun multiplier. So that's why we have adders which have 3 inputs and 2 outputs, and we have a total of 12 adders. We have total of 12 adders. So here, because it is 4 this thing, 4 bits each, so it will be 4 plus 4. Therefore, we'll be having 8 bits in the product, maximum 8 bits. So it is P0 to P7. So that is what is represented in this case. Okay. I think it is time up. I'll continue in the next class. I think we'll be going ahead with what is the speed requirement, what are the bus widths which are required in order to perform the operations. Okay, so that is what we'll be discussing in the coming forth slides. And we'll be discussing something, some building block called as the barrel shifter. So these are the things what we'll be discussing. Okay.